Hi everyone, and thank you for joining me. In today's lesson, we'll explore how to apply multiple transformations to the graph of polynomial functions. Now, many students find this topic challenging for two main reasons. First, it can be difficult to remember how each transformation affects the graph. And second, when several transformations are combined, it's not always clear where to begin. Now, if you've ever felt confused by multiple transformations, you are not alone. The good news is that there is a simple strategy you can use every time. So, by the end of this lesson, you'll understand how multiple transformations work, know the correct order in which we apply them, and be able to determine the image coordinates and sketch transformed polynomial functions with confidence. So, let's get started. Remember that the parents of polynomial functions are in the form f of x equals x to the power of n. Like all functions, polynomial functions can undergo transformations described by the formula f of x equals a f k multiplied x minus d plus c. So as you can see in here, f of x, which appears on both sides of this equation, has changed or is changed by the coefficients a, k, d, and c that we see in different spots in the equation. Now, these coefficients are the ones in charge of transforming the graph of the basic polynomial function or basic any function. Now, when we apply transformations to a function, is similar to simplifying an algebraic expression. And remember that when simplifying algebraic expressions, we use a rule that we call BADMAS. So every operation will have a certain priority. So brackets first exponent, division and multiplication have priority over addition and subtraction. And that's the most important thing we're going to actually focus on and use in applying transformations of polynomials. So first, let's talk a little bit about each and every coefficient. So in what way does each coefficient affect the graph of the function? So we're going to start off with coefficient A. So when a function y equals f of x is transformed by the coefficient A, it means that A is multiplying, in this case, the value of f of x. Now remember that f of x is just another name for y. So what that means is that for the same input value of x, now we're going to have different values of y. So not just f of x, but a value of y that has been multiplied by a number. Now, if this number a happens to be 1, nothing changes. But if this number is greater than 1, say for example 2 or 3 or 10 or 200, imagine that the y values will get greater. So 2 times greater or 100 times greater and so on. So for the same x values, the y values will reach higher, and that can cause the graph of the function to undergo a vertical expansion. In the vertical direction, the function will get taller. That's what that means. So my favorite way of expressing this is by simply stating that the graph undergoes vertical expansion, and I like to add this a little description at the end, but it is not a must. Now, we're going to say that for this section of a values, the function will get taller. Now, what would happen though if instead of multiplying by numbers such as 2 or 3 or 100, as we mentioned, we multiply by -1 or -5 or -100? Well, the y values will still get larger, but they will get larger in the negative direction. So again, this will cause the graph to expand vertically, but in the negative y value. So in this case, then, we're going to say that if a values are less than -1, the function will still undergo a vertical expansion. But since the values of a are negative, and that can happen for any negative a value, we're going to say that the function will change into the negatives. Now, how does this work? So this is something I want to talk about. So let's say that we are here on the Cartesian plane. And we have a point on some graph, and I'm going to call this point right here on the graph of this function. I'm going to bring this a little higher, so right here. So let's say that the graph of this function, so this point is on a function f of x, so it's becoming or is multiplied by -1. So we're not going to go crazy, just change the sign. So for the same value of x, we're going to have a point that is located in the opposite value of y. So it's going to go across the y-axis. So the point will go right here. So in this case, we're going to say that this point has been reflected over this line. So because it's on the other side of this line, which is basically the x-axis. So we call this a reflection over x-axis. Now, another way of saying the same thing is a reflection of the y values. And the reflections of y values happen over the x-axis. So I'm going to write both of them, or of the y values. Now, as you may imagine, if a happens to be 0, imagine multiplying by 0 a polynomial function, let's say 0x to the power of 3, we no longer will have the x to the power of 3 function with the and graph with this specific kind of shape. So, but this will turn into a 0, which is basically a constant function. So a constant function is represented by a horizontal line. So it's going to be basically the x-axis. So this is the reason why we don't take into consideration the values of a equals 0. And again, as we mentioned before, -1 and 1 will not change the value, the stretch of the function. Now, for values of a between -1 and 0 and between 0 and 1, the function will undergo a vertical compression, and that is because the values of y now will be multiplied by numbers less than 1, let's say 1 over 2. It's going to make the graph 2 times shorter. So we're going to move on to the next coefficient, and this is our coefficient k here. Now when a function changes by the coefficient k, it means that a parent of the form y equals f of x is being changed now to become f of kx. So the coefficient k is connected to the variable x, is multiplying the variable x, which means that the variable x is being affected by this new coefficient. And the variable x is a horizontal one, which means that the graph of the function will be affected in the horizontal direction. Now, for example, if you have a value of x equals 1 here, and a k value of 2, then the function will reach the values of, so the function f of 2x will reach the values of x when of x equals 2. So it's going to be the same as f of 2, which is a completely different value. So that will cause the function to undergo a horizontal compression, and the function will get narrower. So we're going to say that if k is greater than 1, the function will undergo a horizontal compression and the graph will get narrower. And for the same reasons that we mentioned for the coefficient a, when k is -1, the function again will get narrower. Now, what happens if the value of k is negative? So if the value of k becomes negative, for example, we have y equals f of -x, we're going to see the same graph with the exact same y values, but appear at opposite values of x. For example, if you have a point right here on the graph of the function f of x, and you are reflecting the x coordinate, so the y value stays the same, and the x value will change to opposite, and the only way that that can change is by going to the other side of the y-axis. So let me write that down here. So we're going to say that in this case, the function will undergo a reflection over the y-axis. And a reflection over the y-axis is similar, or it's the same thing as if saying reflection of the x values. And obviously we do not want k to be equal to 0, and that's like why I made a note in here by drawing an empty circle. That's because if k equals 0, the entire nature of the function will change because x is not going to be playing the game anymore. Now, what happens when the values of k are between -1 and 0 or between 0 and 1? If the values of k are less than 1, then the function will undergo an expansion. So I want you to imagine this way. So if we have the function f of x and it has some point x and y on the graph of it, so when you have a value of 1 over 2 or a coefficient of 1 over 2 multiplying x, whatever x values that we had in here are slowed down by 1/2. So the function will kind of eat up or will digest half of the x that it has. So it will produce weaker or slower y values. So it's going to need bigger x values to reach the same y values that it did in here in this function. So this is better understood when we look at periodic functions, actually, because there are cycles that end at some point, and it's a lot easier to kind of see that this type of transformation. So in other words, we're going to say that because the coefficient k between -1 and 1 kind of slows down the values of x, we're going to need more values of x to reach the same y values as the parent does. And we call this a horizontal expansion because that will cause the function to stretch in the horizontal direction, because horizontal coordinate is the one that is being affected by k. Now, I left the last two transformations, the vertical translations, for last, actually, because I think they are the easiest, so dessert for last. So vertical translations are described by the coefficient c. So what happens when a function undergoes a vertical translation? So if you have the function y equals f of x, that will become y equals f of x and then plus the coefficient c. So as you can see in here, the f of x values are added a number. So which means that all the y values or f of x values you had in the parent now are moving c units. Now, if the value of c is positive, then the graph will move up. So for example, if you have f of x plus 4, that will make the graph of f of x go 4 units higher at every point. And if the value of c is less than 0, it will cause the graph of the function to translate or to move or to shift. These are the common words we use for it, down. Now, next we have horizontal translations. So horizontal translations are indicated by the coefficient d. As you can see, we have a number that we are subtracting directly from x. So what happens when a function is horizontally translated? So the equation of the parent, y equals f of x, in this case, has transformed to become y equals f of x minus, and here we go, we are subtracting the coefficient d. Now, if the coefficient d is positive, and I want to make a note to this, you probably remember the parabolas from grade 10. You should, by the way. So if you had y equals x minus 3 squared, we said that the value of d, or the horizontal translation, was to the right. And that is because we treated this as a part of the equation, and the value of d would be the number that is being subtracted from x, and horizontal translation will happen to the right. So that will make d equal to 3, which is positive. So that means that the graph of this function will move 3 units to the right. If the value of d happens to be negative, so for example, if we have a function that is changed to become y equals f of x, let's say plus 4, it means that we have subtracted from x a negative 4, and that's how we ended up with a plus 4 there. So when you subtract a negative, you see a positive. So, and that tells us that the value of D is negative. So D equals negative 4, which will cause the graph to be translated 4 units to the left. Now, before we leave, remember that reflections can be over the x-axis when A is changing to negative, and reflections are about y-axis when K is changing to negative. So I will continue the rest of the lesson in the next video. I would like to thank you for learning with me as always, and bye for now.